Thanks very much for the invitation. I'd like to talk about some work mostly done by Frank Hu in my group. I want to start with the summary. So the take-home message is that we can get a semi-empirical model, this is on the ANI1 CXX dataset, to agree with DFT to the same level that different ab initio theories agree with one another. So we can put semi-empirical theory in the same box as ab initio on this dataset. The other thing, we're not using black box functions. We're learning one-dimensional functions, so the model is very interpretable. We know exactly what it's doing. Also, we've shown it enough data that showing it more isn't going to help. So I think that means we can measure, use this as to push towards the science of what's the effect of an approximation in semi-empirical Hamiltonian. So as we change Hamiltonian, we'll be able to measure that accurately. And then, if I have time, we'll talk a little bit about our layer, the DFTB layer, as a general component for other models. So we're in the game, like a lot of people here, of can you take properties and learn them, take ab initio data and reproduce it at lower cost. So we're not going to be better than what we're trained to. We're just trying to be cheaper than what we're trained to. And trying to push this idea that artificial intelligence is the right word when you're trying to reproduce humans to be intelligent, but we're trying to reproduce quantum chemistry, so we should call it artificial quantum chemistry. So where does this fit in the history of quantum chemistry? I think there's been these semi-empirical models around for a long time. You embed parameters into the model in order to make them faster, ab initio. Most of the effort over the past decades has been in ab initio. I think we're starting to see effort going back into semi-empirical. And if you look at what's been happening from a bigger perspective, there's sort of two things you can use to lower the cost of a quantum chemistry calculation. One is nearsightedness, and all the linear scaling work, a lot of the advances over the past 4 years have really just been taking advantage of the fact that things become simpler at long range. Taking advantage of similarity has been much harder. It's the basis for semi-empirical models. And I think now we're seeing this rebirth of people trying to use machine learning to take better advantage of similarity. So if you look back 1970s, we had a lot of people developing semi-empirical models. And this was so simple. They had like just a few, 10 parameters and 100 pieces of data. And they got shockingly close to good models of organic chemistry. And I think now we're in a position to go back and redo that, but using large amounts of data and a large number of parameters. So that's the big picture. This, I just want to be referring to this style of neural network. There's been a lot of talks about it already. I just want to make sure everyone is aware of how these work. This is the Baylor-Perinello network. You take the environment of an atom, you build a neural network to producing atom energy, sum up the atom energies to get the total energy. So the only physics in this, and it's not even rigorous, that you break the energy of the molecule into atom energies. That gives you things like size consistency, and then you have features that are invariant, so you get all the symmetry properties if you do it right, but there's very little physics in this model. What we're trying to do is take a quantum chemical Hamiltonian and put machine learning behind the matrix elements into that thing. And I'm showing it here as neural nets, but one of the things, these are so powerful. If you have no physics, a neural net can get the answer. So you may not need something as powerful as a neural net. And actually, all the results I'll show you do not use a neural net. They just use a one-dimensional function. Why would you want to do this? It's because for a minimal basis quantum chemical Hamiltonian, you get all of these things for free. You do not have to learn these properties. As long as you don't have parameters that are completely crazy, you're going to get 4 bonds for carbon. Woodward-Hoffman rules will come out. Various ways to break a bond, aromaticity. All of that will be there. It just won't be numerically precise, but the behaviors are in the model to start off with. So you're giving the thing a big head start. You're learning. And in the history of the sort of views of the machine learning community, building on domain knowledge, if you only have small data, it helps. If you have large data, it hurts. Image recognition for faces used to manually detect the nose and the eyes and all that. When you have enough images, you strip it out, you do better. I think the same thing is what we're going to see here. So how could this fit into the bigger picture? OLS has shown us that with 10 million configurations, you can do amazingly well and end up with an incredibly fast model to predict energy. We only need 10,000 configurations, but our method is fast, but it's not as fast as a neural network. So we could use it, first train a semi-empirical model. If that's not fast enough, use it to generate 10 billion pieces of data and then train a neural net. So that could be where this goes. I also want to emphasize that we are writing a totally separate code to train we're using the DFTB Hamiltonian, and we wrote a separate code to optimize training of that model. We'll transfer the parameters over to standard DFTB codes. And because we want, oops, whoa, I don't know what happened. Yeah. Because we want this to work for people without having to have separate codes, we're sticking to the kinds of the file format that these commercial codes or open, available codes in quantum chemistry. They read the Hamiltonian from Slater-Koster files. And so we're searching over all possible models that can be expressed as a Slater-Koster file. And that gives us this advantage that we just write out the file format, transfer it to DFTB codes. Okay, so what do models look like? They have, that's the wrong slide. Here's the kinds of parameters we're learning. We need to know the orbital energies. We need to know the one-electron interaction term between those orbitals. And we need to know the Coulomb interactions between the orbitals in the molecule. So it's point charge. This is probably the biggest approximation in the Hamiltonian, is that these are just point charges on the atoms rather than multipoles. So the models in the 70s had a more sophisticated Coulomb term. And so specifically for the heavy atoms, we're just doing hydrogen, carbon, nitrogen, and oxygen. There's 4 different functions we need to learn. And they're just functions of the distance between the atoms. So, and they're the symmetry-aligned sp orbital overlaps and Hamiltonian matrix elements. So here's what they look like. Just nice smooth curves that get weaker as you pull them apart. Here's the Coulomb interactions. Initially, we actually coded this up. So we have, it's practical to train, backpropagate through DFTB and train even a sophisticated model like that. It's just way too powerful because you don't need that flexible of a function. So we eventually just dropped back to training one-dimensional functions. Very simple approach. And so that's what it looks like. We need to be able to backpropagate. So we're using ML platforms that give us automatic differentiation to backpropagate through the DFTB. This is what the optimized code looks like. So we spent a lot of time figuring out how to make this really computationally efficient. So that's why it's a separate code you would never use in production. It's really takes the DFTB, and if I have time at the end, I'll talk about how this works and why it's fast. This was the thing that we really spent a lot of time over the past couple of years figuring out. How do we learn these one-dimensional functions? And we're using spline regression. And I think a lot of people know spline interpolation, but regression's similar but a little bit different. It's you choose knots. To define the function, you say, where are my knot points going to be? I'm going to put a 5th-order polynomial between each knot, and I'll have continuity conditions at those knots. And then it turns into a linear model where the values you're getting out, evaluating the spline, is a linear function of the parameters in a B-spline basis. And if you search over all possible values of P, you're actually searching over all possible functions that obey these conditions. So it's a thorough search of the space. The other thing is that the dynamic range of this is huge. It goes from 0 to 250 kcals per mole over the reasonable distances. And if you change it by 0.1, you're adding up so many of these interactions that that's going to give you a change of like 1 kcal per mole. So you need a function that is flexible enough to tune itself to that accuracy, 0.1. And we'll see that that can lead to, we're going to need regularization to have that work out. So we're doing fifth order splines, and we're putting 100 knots in order to get the flexibility we need. It trains pretty fast. One of the things we optimize, we're doing 20,000 configurations. It's, if you were to do, there's a couple codes out there, TB Maltz from the DFTB group, and Sergei Tetryak has a code as well. He basically coded semi-empirical in PyTorch and backpropagate through it. But there's a whole bunch of work that's going on in that code. And you're passing the same molecule through the network thousands of times. So you're doing all of this extra work if you do it every time you pass the molecules through. So we do a pre-compute so that everything that's the same for these, we pre-compute the 20,000 configurations into a tensor structure, and then we can backpropagate without reproducing all of the work of setting up the DFTB. So that's one optimization. The other is that we're doing self-consistent field solutions. How do you handle that in a backpropagation scheme? And what we do is we flip the loop. So we're taking in the Hamiltonian matrices, construct the Fock operator. In the traditional sense, you would do self-consistent iterations till you get the atomic charges of the density matrix converged. And then if you're going to backpropagate the gradient, you have to go through those loops. But you can invert this inner and outer loop so that instead what you do is say, I need the atomic charges to construct the Fock operator. I'll backpropagate through this step for a while, and then every so often I'll stop, every 10 epochs, and redo the self-consistent field calculation. So you've inverted the loops, and now it converges much more quickly. Initially, this is what a learning curve will always look like. At the time you go into convergence, you're barely changing the parameters. So initially, you see the jump every 10 epochs when you redo the charges, but eventually it smooths out. So that's the computational optimization. Here's what happens. If you have 100 knots in a fifth order spline, and you train it, you're going to get something that looks like this. The orange is the derived, DFTB derives its electronic terms from physics, and it looks like the orange curve. And then we train and we get this blue curve. And you would think, here's the performance of the original DFTB model, it's 10 on this data set. You would think that this blue curve would be garbage on test data. It has to be overfit, you would think. Any reasonable person would look at that and say, that can't possibly work on molecules that it didn't see during training. But it does. It works better than the orange. I don't know what this means. I think there's some indeterminacy. This is ANI1 style data, lots of configurations of molecules, and that potential transfers from. You can get it to break a little bit. So here's if you train, this is trained on the same size molecules you test on. If you train on molecules with 1 through 5 heavy atoms, test on bigger molecules, you do not as good, but you're still doing better than the orange. What is going on? But you can't actually tell people to use something that looks like that, so we decided to regularize it. The trick is, every other approach we tried to smoothing would kill your performance. By the time you got it to be smooth, your error, your performance will be way up at 15 kcals per mole error, like really high errors for smooth curves. But if you use a really flexible 1D function and force the second derivative to always point up, then you can get smoothness and enough flexibility that you can get good performance. So it's a very flexible but smooth 1D function. But you still get a little bit of craziness if all you do is constrain the curvature. If you look at this, you get little kinks. And this happens. It's actually something having to do with regressions on splines. Even if you're just fitting a parabola, you can get this with noise in it. You can get this kink behavior coming out. So I don't know what's causing that. It does fix the problem of transfer. So we're able to transfer to new molecules much better if we force it to be regular. But we can also remove those kinks by putting a penalty on the third derivative and adjusting the strength of that penalty to just remove the kink. It hurts your performance a little bit, but not too much. And so you can get very nice looking interaction terms if you both put a curvature derivative, force the curvature to always be of the same sign and penalize the third derivative, which is why we have to go to fifth order splines to get the third derivative to be continuous. This is showing train and test. So the blue is the train data. This is the test. As you add more data, it becomes harder to fit, so the train error goes up. Your test error does better. And if they converge, I think this is a pretty reliable thing that adding more data is not going to do. By the time your train and test data converge, I think adding more data shouldn't help. But if I'm wrong, I'd like to know. Because that, I think, means that this is the limit. We're searching all possible DFTB models that can be expressed in an SKF file format. So we can say that for this data set, this is the best you can ever do with that Hamiltonian. And if we add things to the Hamiltonian, we're in a position to do the science of what gets this error to go down. So there's the DFTB model form itself can be viewed as more general than the SKF. It just requires minimal basis. It only has charge interactions between atoms. And SKF forces these things to be a function of only the distance between the atoms. So we can go to a neural net for these matrix elements while still being DFTB, but we wouldn't be able to write out SKF files and share them with people. And that's a big advantage to be able to do that. So here's the ultimate performance we get. 2.9 kcals per mole, and dipole, I'll show a little more. And if you were to show that to OLS or some neural net person, they would say, wait, 3, that's terrible, I can get you below half. But this is, 1, he needs a lot more data. 2, it's a black box model, so you don't know what it's doing. But 3, look at the data you're training to. So this is a really awesome data set that has all of these levels of theory in it for 250,000 configurations. And if you look at the mean absolute error between them, this is the fanciest method, complete basis set CCSD. So we'll call that the ground truth. If you look at DFTB is pretty bad, starts at 11. But if we train to that ground truth, we get down to 2.9. And if you look at DFT, it's greater than 2.9. MP2 is getting better, but even the lower level CCSDs are worse. So I don't think you can trust any of these numbers to greater than 3 anyway. So if we're getting 3, then I would say we're tied with all the other ab initio methods. If we train to DFT instead, if we treat DFT as the ground truth, we get a comparable accuracy. So we can reproduce either to about 3. So if there's a flaw in this, I also like people's views on, is it true that is it good enough to just be as good on these agreements? We have looked at forces. The forces also have the same level of agreement. So it's not something to do with just energy versus forces. if we can add dipole to the loss function, and we can do much better on dipole before we start hurting the energy. So eventually, to do better on dipole, you're really destroying your performance on the energy, but that's the Pareto bound there. We also train on 2 different randomly pulled sets of molecules from the NE1 data set. And so this is saying you get the same potentials, reasonably. So you can trust the physics that the particular form of these is not hypersensitive to the data you're training to. And the performance is the same across these 2 data sets. So that, All right, so what we're going to do next, we don't have dispersion energy in there yet, and I think we really need to add that. And that should be easy to add D3. I think we'd be able to extend this model to have a split valence data set, and to me that's probably the most important thing. The minimal basis approximation, I suspect, is the biggest approximation in these Hamiltonians, although maybe it's going to dipole-dipole interactions between atoms. I think to be able to break bonds, we'll need some model that has the behavior you need to be homolytic cleavage, and GVB is what I think would be 1. But if anyone has, the model doesn't have to be numerically accurate. It just has to have the right behavior. And we can train the accuracy in if it has the right behavior. So I think GVB is the right one. I really want to move on to transition metals. And I was going to talk about the component of this, like how it could be useful in other things. But if you're interested in that, talk to me. I'd rather leave time for questions. So I'll just finish there. I'll put up the summary again that I started with. Thanks.
Very interesting talk. I was wondering, the arrows you showed are on energies, right?
Yeah.
What are the arrows on forces?
The reduction in error is almost, so if you looked at DFTB out of the box versus our trained one, the reduction is a little bit less than on energy. So we're reducing the error on the energy by 60%, and I think we get about 50% reduction in forces. I suspect we'd do better if we trained on forces explicitly. But, yeah.
Have you tried specifically some, I don't know, some dihedral scans on conjugated molecules or something like that to see if it works?
No, we should. That would be, yeah, definitely. Even just with this model, we should characterize it more. We did compare a lot to other techniques like Sergei Tetriak's results, and he uses a neural net as an input to the quantum, and we do better than him in general, except on one property. Yeah.
Okay. Thank you very much.
Hi, thanks for the very interesting presentation. You've shown your matrix elements and how they vary with distances and so on, and they, in the end, like once they're trained and smoothed out, they look very similar to the DFTB matrix elements. And I was wondering, so from your training curves that you've shown, you get right, your error starts are relatively large. That suggests to me that you're training your parameters from scratch. You're not starting from. Are you starting from?
No, we're cheating a bit. We're starting from DFTB, so it might be.
Okay.
That's another thing we should do is start from a random starting point and see what happens.
Okay. It was exactly.
It might be that they look similar because we started from there. The other thing I forgot, we are training both the Hamiltonian and the overlap S. So, and that could be why we're getting the crazy behavior. There might be that H and S are coupled in some way, so when one goes up, the other goes down. We have to try seeing if that's the origin of the weirdness. Yeah.
Okay, thank you very much.
So you showed, oh wow, a little close. You showed the weird wobbles that you started with. And I guess I had two related questions. One is, why 100 knots? That feels very large, but I assume that there's a good reason for that. And my second follow-up from that is, given all these constraints that you've had to put on the spline to make it behave well, does that suggest maybe there's a better basis to expand these functions and that might be easier to train?
Yeah. Well, easier to train, I don't know. It trains fine. But it has to do with a change that's so small you could never see it on this plot matters a lot. And so 50 knots is almost enough. But because the regularization is so strong that forcing it to curve up, going from 100 down to 50 doesn't really change the result much, doesn't change the behavior of the model much. So, and going to 200 doesn't help, so that's why it really does saturate by 100 knots.
Dave, quick question. So to get from 2.5 to 0.5, right?
Yeah.
Do you see how to get there? Is it because of the simplifications in the Hamiltonian itself? Or is it basis set, maybe?
I think in the SKF format, this is the best you're going to do. When we tried neural nets, we had to regularize like crazy, but we never got better than 2.5 anyway. So I don't think a more flexible model form for the matrix elements themselves is going to help. I think it's either that we need to go beyond point charges to. The other thing we don't have D3 dispersion, and maybe that's going to help, but in the bigger molecules. But I don't know. I think without having the split valence, without having the electron distribution being able to breathe, I think you're going to be limiting what you can do. So that's the highest priority for me, is to get, plus it would be cool, split valence, semi-empirical would be pretty.
Thank you.
Thank you for a very nice presentation. I was thinking maybe if you can comment on the multi-reference or the need for the multi-reference method. So I guess the traditional method of treating this in semi-empirical methods is the half-electron method, or like Fermi smearing, like they do in the XTB method. So do you think it's like necessary to go to a more explicit multi-reference treatment?
I think this in a coding implementation perspective, this is going to be harder from the way that we do the pre-compute. Everything that's post-Hartree Fock, we have the full Fock operator after. So we can do any, I think single CI for excited states might be a good thing to do next, because that would be easy. And I don't know enough about GVB to know how hard it would be. But I think anything that's just linear algebra is really easy to code in these platforms. So I think we can do a lot and be able to backpropagate through it fine.
Okay, thank you. And I also had another question about, like, given that you don't need too much training data for this, how easy would it be to expand it to, let's say, the full periodic table?
Oh, I'm not sure the question of, yeah, if we were to go to something like this, then I think that the data capacity would go up, and we'd need more data to train it.
Mm. Okay. Thank you.
It's also too easy, maybe, that these are just vibrating molecules. We're not breaking any bonds or anything interesting yet.
Yeah, thanks. So exciting talk. So I agree that the minimal basis is probably what is handicapping your accuracy. However, now, like, talking about the roughness of these matrix element curves, this raises the question: did you try geometry optimization? Because that would probably affect. Like, I'm betting that, like, these kinks, they happen because of your training geometry. So, like, it is adapting the Hamiltonian to these specific geometries.
Yeah.
So yeah, like, the ultimate test would be, like, to see what happens then when you let the geometry relax. Like, are you maintaining the same level of accuracy or not?
That's a good, yeah, I think it'd be interesting to try. I mean, it's not, I mostly included that in the talk because I think it shows that you can have good transfer doesn't mean your model is reasonable. You know, we're doing the same test everyone else does for transfer, and we can show that the model looks like garbage but transfers. And so, yeah, we have a solution to it, but I do think it's interesting to know that transfer is not a good measure. That you can have physically crazy models that transfer fine. It's weird.
Building on the previous questions, have you tried either learning instead of the entire curve, the difference between a reference one, just so you learn just a small difference? Like you take as a reference the default parameters, and then you learn the difference between.
I wonder, to me, because it's a linear model, the spline model, I think that would just be equivalent to adding a matrix multiply on.
But then you can regularize.
Oh, a different form. Actually, we did, when we do the neural net, then we regularize by deviation from the physics-derived DFTB curve, and it oscillates around that curve,
Okay,
which makes us nervous.
And another thing would, maybe it would be useful to learn a function of the inverse distance instead of the distance.
Oh, that we should talk about.
Or the
actually,
y-axis,
Yeah.
you can put it in log scale.
Yeah. We tried non-uniform knot spacing, which might be similar, and that didn't really, it mattered if you're not regularized, but if once you have the curvature up, then rearranging the knots to be like the same number of data points between each knot doesn't change anything.
Okay.
Okay, so let's thank David once more.